Welcome to this lecture on designing efficient NPUs. In this talk, we'll explore architectural choices that matter most when building neural accelerators, from memory hierarchy to interconnects and power management. I'll walk you through practical techniques that help hardware and software work together, with examples and trade-offs you can use when evaluating or designing an NPU. This slide shows how a dedicated accelerator fabric integrates with host processors to offload repetitive MAC loops. Picture an NPU sitting beside CPU, GPU, and DSP cores, receiving pre-processed tensors, executing layers locally, and returning results, while a low latency interconnect ties it to shared DRAM or last-level cache to minimize costly data movement. Here we focus on SIMD parallelism and an efficient data flow that keeps hundreds of MAC units busy every cycle. The 2-dimensional SIMD array streams tiles of activations and waits via a dataflow controller, which reduces register, spills, and control hazards. The overall idea is to exploit massive parallelism while minimizing bottlenecks that would starve compute units. This slide explains a 3-level memory hierarchy and latent SIU hiding strategies used in NPUs. Higher bandwidth off-free chip memory feeds a shared memtile and then local SRAM scratch pads, enabling tiling and doubly buffering to overlap loads and computation. The result is zero store computation in practice, where careful tiling hides DRAM latency and sustains continuous throughput. The Packetose switched network GUN chip, or NO-C, is shown here as the transport fabric connecting PE clusters to memory banks. Quality of service arbiters enable deterministic real-time streams alongside best effort traffic, preventing data jams while filling spare bandwidth. Think of it as a high-speed highway with reserved lanes for latency-sensitive traffic and flexible lanes for bulk transfers. This slide highlights precision quantization as a primary lever for increasing ops per cycle and cutting energy. Moving from FP32 to INT4, INT8 or BF16 can multiply throughput while dramatically reducing power, provided you use noise-tolerant training and quantization-aware techniques to preserve accuracy. This enables both low-W power edge inference and high-W volume generative workloads efficiently. The optimal tile parameters slide shows how balancing compute cycles with DMA transfer time yields a performance knee point. Tile sizes affect both the compute curve and memory curve, and analytical models find the intersection where throughput is maximized. Tuning these parameters minimizes DRAM traffic and helps achieve high TOPS on real hardware without bottlenecking memory. This slide covers finer-grained sparsity techniques that save compute and storage. Activation sparsity skips zero-valued activations to reduce MACs. Hardware bitmaps compress on new chip weights, and pointer-based pipelines fetch only non-zero blocks, maintaining throughput without memory bloat. Together, these mechanisms reduce computational load and storage cost while preserving performance on pruned models. First-generation NPU designs often ran into a CPU offload bottleneck, creating a data traffic jam between accelerator and host. Unsupported large tensors forced the CPU to intervene, increasing latency, wasting power on data movement, and complicating scheduling. The takeaway is that efficient NPUs must minimize host involvement to preserve accelerator gains and deliver predictable performance. This slide presents the architectural trade-off between full reconfiguration and hardened logic reuse. Reconfiguration gives flexibility to support new operators but adds overhead and latency, while hardened kernels deliver deterministic, low-W latency performance with minimal runtime cost. Architects need to balance future-proofing against the requirement for predictable, real-time operation in target use cases. Power delivery and thermal management are critical for sustaining throughput, as shown here. Independent voltage scaling for tensor units can cut dynamic power significantly, while dark silicon analysis and duty cycling help keep junction temperatures under 85 degrees Celsius in fanless designs. The goal is to optimize voltage and temperature so the NPU can hit sustained peak performance without thermal throttling. This slide summarizes practical design flows. A parameterized RTL generator produces different PE array sizes while preserving compiler intrinsics and versioned ISA extensions. Let firmware add quantized ops without a full kernel rewrite. Together, these approaches enable silicon refreshes and scaling across product variants while minimizing software disruption and preserving a unified software stack. Efficient multi-model execution relies on time-sliced partitioning, fast context switching, and QoS controls to allocate max slices and SRAM banks per model. This enables concurrent tasks like vision, voice, and generative inference to meet their respective deadlines and latency targets on a single NPU. The architecture supports deterministic performance by combining partitioning with per-model resource knobs. The final slide emphasizes CoE optimization across algorithms, compilers, and hardware as the key to turning raw TOPS into real performance. Tiling, memory placement, and instruction scheduling in compilers must feed hardware features like on-chip memory and interconnects, while continuous feedback loops guide architecture choices. In short, tight hardware-software collaboration turns transformer bottlenecks into silicon features.